Since the invention of the telescope, few stars have attracted more attention than Alpha Centauri. Located just 4.37 light-years from Earth, it is our closest stellar neighbour and the destination most often proposed in serious discussions of interstellar travel. In August 2024, a new observation raised an unexpected possibility. Using the mid-infrared instrument aboard the James Webb Space Telescope, astronomers detected a faint point of light near Alpha Centauri A. The object appeared more than 10,000 times dimmer than the star itself, and lay at a distance of roughly 2 astronomical units, within the region where temperatures could allow liquid water to exist on a planetary surface. If it was a planet, it would have been one of the most important exoplanet discoveries ever made. But when Webb observed the system again in February and April 2025, the mysterious signal had vanished. What appeared briefly in one of the most closely watched star systems in the sky remains unexplained. The system next door. Alpha Centauri is not a single star. It is a triple stellar system, and the distinction matters enormously for understanding both why the system has attracted so much scientific attention and why it has resisted every serious attempt at planetary detection. At the center of the system sit 2 Sun-like stars designated Alpha Centauri A and Alpha Centauri B. These 2 stars are locked in a gravitational orbit around their shared center of mass with a period of 79.91 years, following an elliptical path that carries them between 11.2 and 35.6 astronomical units apart over the course of each orbital cycle. For reference, 11.2 astronomical units is slightly larger than the distance between the Sun and Saturn. 35.6 astronomical units approximates the distance between the Sun and the inner boundary of the Kuiper Belt. The 2 stars spend their entire existence in a slow gravitational waltz, sometimes drawing close enough to influence each other's planetary neighborhoods significantly, sometimes separating to distances where each star has more room for stable satellite orbits. Alpha Centauri A is a G2-type main sequence star with a mass approximately 1.1 times that of the Sun, a radius about 1.22 times solar, and a luminosity roughly 1.519 times the solar luminosity. Its surface temperature sits at approximately 5,790 Kelvin, nearly identical to the Sun's 5,778 Kelvin. It is estimated to be between 5.3 and 6.8 billion years old, placing it in the mature phase of its hydrogen-burning main sequence life. In almost every physically relevant property, Alpha Centauri A is a near twin of our own star, slightly larger, slightly brighter, slightly older, but built from the same spectral class, burning fuel through the same proton-proton chain fusion process, and radiating light across the same wavelength distribution. Alpha Centauri B is a K1-type star, slightly cooler and less massive than its companion. It carries approximately 0.907 solar masses, a radius of about 0.86 solar radii, and emits roughly 0.5 times the solar luminosity. Its surface temperature is approximately 5,260 Kelvin. K-type stars are sometimes called orange dwarfs, though Alpha Centauri B sits near the boundary between G and K classifications and appears only marginally redder than the Sun. It is a legitimate Sun-like star by any reasonable astrophysical definition. The third member of the system, Proxima Centauri, orbits the central pair at a distance of approximately 12,950 astronomical units, which is about 0.21 light-years. Proxima completes one orbit around Alpha Centauri A and B every 547,000 years, according to current estimates. It is a red dwarf of spectral type M5.5V, with a mass of only 0.1221 solar masses and a luminosity roughly 0.0017 times that of the Sun. It is so faint that despite being the single closest star to Earth at 4.243 light-years, it cannot be seen without a telescope. Proxima has received enormous scientific attention because it hosts 3 confirmed planets, including Proxima Centauri B, which orbits within its habitable zone. But Proxima is a fundamentally different kind of star, a violent, flare-prone red dwarf that subjects its planets to ultraviolet and X-ray bombardment orders of magnitude more intense than what Earth receives from the Sun. Whatever relevance Proxima's planets have to astrobiology, they do not answer the central question about the Alpha Centauri system. Do Sun-like stars, with spectra and luminosities comparable to our own Sun, host planets around the nearest example of their kind? This is the question that defines the scientific significance of the system, and as of today, the answer remains unconfirmed. The system blazes as the 3rd brightest object in Earth's night sky, trailing only Sirius and Canopus. It sits in the constellation Centaurus, permanently below the horizon for most of the northern hemisphere, but visible year-round from latitudes south of roughly 29 degrees north. Ancient Babylonian astronomers catalogued it. Ptolemy included it in the Almagest in the 2nd century. Aboriginal Australians incorporated it into navigational traditions and cosmologies. Every civilization with a view of the southern sky knew this star. We have been watching it for as long as we have been watching anything. And for all of that watching, we have never confirmed a single planet around either of its Sun-like members. The nearest stellar neighbourhood containing Sun-like stars remains, in terms of confirmed planetary inventory, completely blank. What Webb attempted to change that blank, and what it found instead of a clean answer, is the subject of everything that follows. The proximity paradox. Common sense says that the closer an object is, the easier it should be to study. A rock in your hand reveals more detail than a rock across the street. A mountain 1 kilometre away shows more texture than a mountain 100 kilometres distant. Distance costs resolution, costs photons, costs information. Every branch of observational science operates under this principle, and telescopic astronomy is no exception. Larger mirrors, better detectors, and higher resolution instruments are the standard response to distance. You build better tools to compensate for the attenuation that space imposes on faint signals. Alpha Centauri inverts this reasoning entirely, and understanding why it does so is essential to understanding why Webb's observation was so technically extreme. The problem begins with brightness. Alpha Centauri A has an apparent magnitude of approximately -0.01 as seen from Earth, making it one of the most luminous objects in the sky. Its apparent brightness is not a product of intrinsic power alone, it is a direct consequence of proximity. A Sun-like star blazes with roughly 3.83 times 10 to the 26 watts of radiated power. At 4 light-years, that output translates to an apparent brightness that saturates sensitive astronomical detectors, floods coronagraphic instruments with residual scattered light, and overwhelms the faint signatures that planetary companions would produce. Alpha Centauri A is not unusually luminous as stars go. It is simply much closer than almost anything else, and that closeness turns its ordinary stellar output into a wall of light that instrument designers have spent decades trying to penetrate. For radial velocity surveys, the brightness of the target is not itself the primary problem. The radial velocity method measures Doppler shifts in stellar absorption lines caused by the gravitational tug of an orbiting planet, and brighter stars actually provide more photons per unit time, improving the signal-to-noise ratio of individual spectroscopic exposures. The problem for Alpha Centauri is not its luminosity, but its binarity. Alpha Centauri A and B orbit each other with velocities that are orders of magnitude larger than the radial velocity signal a planet would produce. A Saturn mass planet at 1 astronomical unit would induce a stellar reflex velocity of roughly 30 to 40 meters per second. The binary orbital motion of the two stars relative to each other involves velocities of several kilometers per second. Before any planetary signal can be extracted, the entire binary orbital velocity must be modelled and subtracted from the data with extraordinary precision. Any error in that subtraction, any misestimate of the binary parameters, leaves residual noise that can mimic or conceal a planetary signal entirely. For transit photometry, proximity creates its own unique difficulty. The stars are so bright that photometric precision is limited by systematic detector effects rather than by the shot noise of individual photons. A planetary transit across Alpha Centauri A would produce a brightness dip of roughly 0.01% for an Earth-sized planet. Achieving that precision from the ground against a target this saturating is exceptionally difficult. From space, the problem is different but related. Photometric missions like Kepler and TESS are designed around targets several magnitudes fainter. Pointing them directly at Alpha Centauri produces images where the stellar point spread function bleeds across multiple detector pixels, complicating the extraction of precise light curves. For direct imaging, the proximity problem is perhaps most acute. Direct imaging requires spatially resolving a faint planet from the bright disk of its host star. The relevant quantity is angular separation. How far does the planet appear from the star on the sky? A planet at 1 astronomical unit from Alpha Centauri A would subtend an angular separation of roughly 1 arcsecond as seen from Earth, which is in principle resolvable by large telescopes. The problem is contrast. The planet is roughly 10,000 to 100,000 times fainter than the star in the mid-infrared, and the star's light, scattered and diffracted by the telescope optics, fills the angular region where the planet would appear with a structured glow that can easily exceed the planet's signal. Suppressing this stellar halo to the levels required for detection demands coronagraphic technology of the highest quality, operated from a thermally stable platform, with careful calibration of the instrument's optical response. All of these problems are compounded by the binary. No coronagraph can simultaneously block both Alpha Centauri A and Alpha Centauri B. The second star sits at a projected angular separation that has varied from about 4 to about 22 arcseconds over the course of its 79.91-year orbit. When the stars are close together on the sky, their scattered light patterns overlap into an entangled mess that no post-processing pipeline can fully disentangle. When they are well separated, the second star still contributes a bright contaminating halo across the same field of view where a planet around the primary would be found. Every observational approach must account for 2 stars rather than 1, doubling the noise floor and shrinking the region of the image where detections are reliable. This is the proximity paradox in its full expression. Alpha Centauri is exactly close enough that its light overwhelms every standard technique for planet detection. Not so close that it fills the sky, not so distant that it fades into tractable faintness, but at precisely the distance where a sun-like star's luminosity intersects with the sensitivity limits of our instrumentation in the most punishing possible way. The nearest sun-like stellar system is, by a cruel coincidence of physics, one of the hardest planetary systems in the sky to characterize. Decades of failed detections. The history of planet searches at Alpha Centauri is long enough, and the parade of false positives prominent enough, that it constitutes a field within a field. A specialized literature documenting the repeated collision between scientific ambition and the system's specific technical resistance. Understanding this history is not merely context. It is evidence of just how formidable the detection problem is, and it gives Webb's 2024 observation its full weight. The first serious era of targeted planet searches at Alpha Centauri began in the 1990s, coinciding with the launch of modern high-precision radial velocity spectrographs. The instrument that would define the field for the next 2 decades was the High-Accuracy Radial Velocity Planet Searcher, or HARPS, installed in 2003 at the European Southern Observatory's 3.6-metre telescope at La Silla Observatory in Chile. HARPS achieved radial velocity precision of roughly 1 metre per second, sufficient in principle to detect planets of a few Earth masses orbiting within a few astronomical units. The Alpha Centauri binary was among its priority targets. In October 2012, the results from the HARPS Alpha Centauri monitoring program led by Xavier Dumusc at the Geneva Observatory were published in Nature. The team reported the detection of a planet with a minimum mass of 1.13 Earth masses orbiting Alpha Centauri B with a period of 3.236 days at an orbital separation of roughly 0.04 astronomical units. The announcement was global news. The nearest Sun-like star had an Earth mass planet. Scientific and popular press declared it the most important exoplanet discovery since the first confirmed extrasolar world around a Sun-like star. It was named Alpha Centauri B. By 2015, the detection was effectively retracted. Independent analyses by multiple groups demonstrated that the reported signal was most likely an artifact of the data analysis procedure rather than a real planetary companion. The methodology used to subtract the stellar activity signal from the radial velocity data introduced periodic noise at timescales similar to the claimed planetary period. Different statistical treatments of the same dataset produced contradictory results. Some analyses recovered the signal. Others found it consistent with zero planetary amplitude. The consensus that emerged from the subsequent literature was that Alpha Centauri B was a data processing artifact, one of the most visible false positives in the history of exoplanet science. The failure of Alpha Centauri B illustrated the specific danger of searching for planetary signals buried beneath large systematic noise in binary systems. Radial velocity surveys continued at Alpha Centauri using improved instrumentation. The espresso spectrograph, installed on the Very Large Telescope at Paranal Observatory in Chile and operational since 2018, achieves radial velocity precision approaching 10 centimeters per second. It has been used to monitor both Alpha Centauri A and B. As of the most recent published analyses, no confirmed planet has emerged from these observations. Upper limits on planetary mass at specific orbital periods have been derived and published, providing constraints on what does not exist. But no detection has survived the scrutiny required for confirmation. Transit searches fared no better. A dedicated photometric mission called Tiny Transiting Exoplanet Surveyor, or TTS, was proposed specifically to monitor Alpha Centauri from space for transiting planets. The Canadian Space Agency mounted a brief observing campaign using the MOST satellite in 2013 and 2014. No transits were detected. The geometric transit probability for a planet at 1 astronomical unit is approximately 0.5%, meaning that unless a planet's orbital plane happens to be favorably aligned with Earth's line of sight, no transit will ever be observed, regardless of how sensitive the photometry becomes. The ground-based direct imaging attempts began in earnest, with the commissioning of dedicated infrared instruments on large telescopes. The most significant pre-Webb effort came from a team led by Kevin Wagner at the University of Arizona. Using an instrument called Near Agena Resonance Imager and Spectrograph, or NEAR, installed on Unit Telescope 4 of the Very Large Telescope, and commissioned in 2019 specifically for the Alpha Centauri campaign, the team observed the system for approximately 100 hours over several weeks in May and June of 2019. NEAR was a product of a collaboration between the European Southern Observatory and Breakthrough Watch, the observational arm of the Breakthrough Initiatives program, and it was specifically optimized to search for planets in the habitable zones of the two Sun-like stars at mid-infrared wavelengths of approximately 10 to 12.5 micrometers. The campaign produced a tentative result. A faint source appeared in the processed images near Alpha Centauri A at a projected separation of approximately 1.1 astronomical units. This source was designated the candidate, or C1. The team published their results in 2021 in Nature Communications, describing C1 as consistent with a Neptune to Saturn mass planet in or near the habitable zone. But they were careful to note that the observational arc was too short to determine whether C1 was moving in a manner consistent with an orbiting planet, and that alternative explanations, including warm exozodiacal dust and instrumental artifacts, could not be ruled out. C1 was filed in the scientific literature as an intriguing but unconfirmed result. Without follow-up confirmation, it attracted interest but changed no conclusions. That is the state of affairs that existed before Webb turned toward Alpha Centauri in August 2024. Decades of observations, 0 confirmed planets. 1 retracted Earth mass planet, 1 ambiguous infrared source. A system that had absorbed more scientific effort per confirmed exoplanet than any other nearby target and yielded nothing conclusive. What Webb attempted to do in that context, and what it found, represents either the beginning of a resolution or the deepening of a mystery. Why Webb pointed here? The decision to use the James Webb Space Telescope to observe Alpha Centauri was not a casual targeting choice. Webb's observing time is among the most contested scientific resources on Earth. Every hour of observation the telescope performs is granted through a competitive proposal process evaluated by peer review committees. Time is finite. Demands are enormous. Targets are chosen because they offer scientific return that cannot be achieved any other way. The Alpha Centauri campaign was proposed, evaluated, approved, and executed because the specific combination of instrument capability and scientific target created an opportunity that no previous observatory had ever possessed. The instrument at the center of this observation is MIRI, the mid-infrared instrument. MIRI operates at wavelengths between 5 and 28 micrometers, deep in the infrared portion of the electromagnetic spectrum far beyond what human vision can detect. It was developed jointly by NASA and a European consortium, built by a team of over 200 scientists and engineers across 10 European countries and the United States, and cooled by an active cryocooler to approximately 6.4 Kelvin, colder than any other component on the telescope. At these temperatures, MIRI's own thermal emission is suppressed to levels low enough that it can detect the faint infrared glow of warm astronomical objects without being swamped by its own instrumental heat. The wavelength choice is strategically crucial for planet detection. In visible light, a sun-like star outshines a gas giant companion by a factor of roughly 1 billion. No coronagraph yet built can suppress starlight to 1 part in a billion. In the mid-infrared, the contrast ratio collapses dramatically. A warm gas giant at a temperature of 200 to 400 Kelvin radiates relatively more of its total energy at these wavelengths than the host star does. The host star still dominates, but only by a factor of thousands rather than billions. This shrinking contrast gap is what makes mid-infrared coronagraphy the most promising near-term path to directly imaging planets in the habitable zones of nearby sun-like stars. MIRI includes a 4-quadrant phase mask coronagraph, a device that imposes a carefully engineered phase shift on incoming starlight to cancel it through destructive interference. This coronagraph operates at wavelengths of 10.65, 11.4, 15.5, and 23 micrometers. For the Alpha Centauri observation, the team used the 15.5 micrometer channel. At this wavelength, the inner working angle of the coronagraph, the minimum angular separation at which starlight suppression is effective, corresponds to roughly 0.33 arcseconds. At Alpha Centauri's distance of 1.34 parsecs, this angular limit translates to a physical separation of approximately 0.44 astronomical units from the host star. Objects orbiting closer than that cannot be detected. Objects farther out fall into the zone where the coronagraph can suppress the stellar glare enough to reveal faint companions. One astronomical unit lies comfortably beyond this inner working angle. The entire classical habitable zone of Alpha Centauri A, which spans from roughly 1.2 to 2.2 astronomical units based on stellar flux calculations, sits within the accessible field. MIRI's coronagraph at 15.5 micrometers could in principle detect a Saturn mass gas giant at any point in Alpha Centauri A's habitable zone, provided the starlight subtraction performed well enough and the planet was thermally luminous enough to rise above the noise floor. The scientific case for attempting this observation rested on three pillars. First, the system's proximity means that any directly imaged planet would offer follow-up characterization opportunities unmatched anywhere else in the galaxy. The angular size of the planet's orbit, its proximity to Earth, and the brightness of the host star all translate into spectroscopic and photometric signal-to-noise ratios that would be orders of magnitude more favourable than for any other known exoplanet system. Second, the near 2019 observation had produced a candidate, albeit ambiguous, suggesting that a detectable source might actually be present if a more capable instrument looked. Third, no other instrument in the world, or above it, could achieve the combination of mid-infrared sensitivity, space-based stability, and coronagraphic performance that MIRI brought to this problem. The team that proposed and executed the observation included Aaron Carter at the University of California, Santa Cruz, Charles Beichmann at the NASA Exoplanet Science Institute at Caltech, and Anurup Banu at the California Institute of Technology, along with a collaboration of co-investigators. They were granted observing time through the Director's Discretionary Program, which allows the Space Telescope Science Institute to allocate observation windows for scientifically urgent targets outside the standard proposal cycle. The observation parameters were set to maximize sensitivity at the habitable zone separations most relevant for planetary detection. Exposure times, reference star observations, and data reduction strategies were all designed around the specific challenge of extracting a faint source from the overwhelming glare of the closest pair of sun-like stars to Earth. Everything about the program was built for one purpose: to answer whether Alpha Centauri A has something orbiting in the region where a planet could in principle hold liquid water on its surface. Target acquisition at the limits of Webb. Every James Webb Space Telescope observation begins with a procedure called target acquisition. The telescope's fine guidance sensor locks onto the intended star, measures its position relative to a grid of reference points, and confirms alignment to within fractions of an arc-second before the science instrument begins collecting data. For most targets, this process is routine. The fine guidance sensor works across a broad range of stellar brightnesses. The acquisition takes a few minutes, and the observation proceeds. For tens of thousands of targets observed since Webb began science operations in 2022, the procedure has worked without incident. For Alpha Centauri A, the standard target acquisition protocol fails immediately. Alpha Centauri A is too bright. The fine guidance sensor is designed for stars within a certain brightness range, and Alpha Centauri A sits far outside the bright end of that range. Directing the telescope to stare directly at Alpha Centauri A for the purpose of acquiring it would saturate the guidance sensor in milliseconds, flooding it with so many photoelectrons that the readout electronics lose the ability to determine where the star is centered in the field. The automated system would declare the acquisition failed and terminate the observation before any science data were collected. The operations team at the Space Telescope Science Institute developed a custom observing sequence specifically for this target. The solution was a technique called a blind offset. Instead of acquiring Alpha Centauri A directly, the telescope first locked onto a nearby reference star faint enough for the guidance sensor to handle. For this observation, the reference was Epsilon Muscae, a red giant in the constellation Muscae, lying approximately 340 light-years from Earth and approximately 2.4 degrees away from Alpha Centauri on the sky. Epsilon Muscae is bright enough to provide a reliable guidance sensor lock, but falls well within the sensor's operational range. Once the telescope had confirmed its alignment on Epsilon Muscae, the operations team commanded a pre-calculated angular offset in right ascension and declination designed to move Alpha Centauri A to the position of the coronagraphic mask inside Miri. The telescope executed this slew without looking at its destination. The guidance sensors remained on Epsilon Muscae throughout, tracking the reference star while the rest of the telescope's optical axis pointed toward Alpha Centauri. The coronagraphic mask received Alpha Centauri A's light based entirely on the precision of the offset calculation and the stability of the telescope's attitude control system. The required precision for this procedure is approximately 20 to 50 milliarc seconds. An error larger than that would place Alpha Centauri A off-center behind the coronagraphic mask, allowing stellar light to leak around the edges of the phase mask and contaminate the field. The phase mask coronagraph requires the target star to be centered to a small fraction of the mask's dimensions to achieve its rated suppression performance. A miscentered star produces significantly more residual light than a well-centered one, potentially erasing any faint planetary signal beneath a structured halo of incompletely suppressed starlight. The Webb attitude control system routinely achieves pointing stability at the arcsecond level during normal slews. Maintaining the much tighter milliarc-second precision required for coronagraphic observations requires the fine guidance sensor to make continuous small corrections to the telescope's orientation. With the guidance sensor locked on Epsilon Muscae rather than Alpha Centauri A, those corrections were referenced to the reference star rather than the science target. Any drift or error in the assumed angular relationship between Epsilon Muscae and Alpha Centauri A would directly translate into a centering error on the coronagraphic mask. This approach worked. The custom sequence placed Alpha Centauri A behind the mask with sufficient accuracy to achieve useful coronagraphic suppression. But the complexity of the workaround reveals something important. Alpha Centauri A is not a target that Webb's operational infrastructure was designed for. Every step of the observation required bespoke engineering, from the acquisition strategy to the tracking parameters to the downstream data reduction pipeline. The observation was a custom instrument built around a custom star using a custom procedure, and even so, the resulting data contained residual artifacts and complications that required months of careful analysis to address. The difficulty of pointing alone before a single photon of science data was collected established the character of what Webb was attempting. This was not a routine survey observation aimed at a cooperative target. It was an assault on the hardest observational problem in the nearest stellar system, pressed to the very boundary of what the telescope and its instruments could physically accomplish. The light that hides everything. With Alpha Centauri A placed behind Miri's coronagraphic mask and the instrument collecting photons at 15.5 micrometers, the data reduction team faced a challenge that no previous Webb program had required solving in quite the same form. Suppressing the light of a single sun-like star is already among the most technically demanding tasks in observational astronomy. Suppressing the light of two sun-like stars simultaneously, while searching for a point source thousands of times fainter than either, sits at the frontier of what is physically achievable. The four-quadrant phase mask coronagraph that Miri uses works by dividing the focal plane into four quadrants, each separated by a pair of orthogonal opaque boundaries. The mask applies a phase shift of pi radians to the light, passing through two diagonally opposite quadrants, while leaving the other two quadrants unshifted. For a star centered precisely on the mask, the destructive interference between the phase-shifted and unshifted portions cancels most of the stellar light. What emerges is a structured residual pattern, rather than the overwhelming direct stellar beam. The residual pattern is not uniform darkness. It contains bright features, a cross-shaped diffraction pattern aligned with the quadrant boundaries, concentric rings from the telescope's secondary mirror and support structure, and a halo of scattered light from imperfections in the telescope's mirror surfaces. These features are bright relative to a faint planetary companion. At 15.5 micrometers, the residual starlight pattern from Alpha Centauri A after the coronagraph produces a brightness distribution that varies across the field but can be comparable to or brighter than the expected signal from a Saturn mass planet at several of the most sensitive positions in the image. To separate a real planetary companion from this structured noise, astronomers rely on reference star subtraction. The principle is straightforward. Observe a star with similar brightness and spectral properties to the science target. Use the same coronagraphic setup and exposure parameters, and then subtract the reference observation from the science observation. Because both stars produce similar diffraction and scattering patterns through the same optics, the subtraction removes the common mode stellar halo and leaves behind any sources unique to the science target, including any planetary companion. For the Alpha Centauri observation, reference star subtraction was performed using observations of multiple reference stars selected to match Alpha Centauri A's properties as closely as possible. The subtraction pipeline was applied to the full dataset, peeling away the layered structure of the stellar halo one reference at a time and combining the residuals to minimize noise. This process reduces the effective noise floor considerably, but it does not eliminate it. Imperfect color matching between the science target and reference stars, slight differences in the instrumental response between observations, and the intrinsic variability of the residual diffraction pattern leave behind signal in the subtracted image that is not associated with any real astrophysical source. Alpha Centauri B compounds this problem substantially. The second star sits at a projected angular separation from Alpha Centauri A that, during the August 2024 observation, was approximately 10 arcseconds. The coronagraph is centered on Alpha Centauri A. Alpha Centauri B sits fully in the field of view, unmasked, radiating its own mid-infrared flux into the detector. Its light passes through the same optical system, generates its own diffraction pattern, contributes its own scattered halo, and overlaps with the residual pattern from Alpha Centauri A in the region of the field that is most scientifically important for planetary detection. Removing Alpha Centauri B's contribution requires constructing a model of its point spread function at the appropriate position in the field and subtracting that model from the image. This model is derived partly from the reference star observations and partly from the known optical properties of the mirror instrument at the relevant wavelength. The subtraction of a bright off-axis star from a coronagraphic image is a standard technique in direct imaging analysis, but it introduces its own residuals. Any mismatch between the assumed and actual point spread function of Alpha Centauri B leaves a structured residual at and around its position that can create or suppress apparent point sources in the science field. The team worked through all of these layers. Reference star subtraction for Alpha Centauri A. Point spread function subtraction for Alpha Centauri B. Residual noise characterization across the accessible field. Systematic artifact identification using knowledge of the instrument's known optical anomalies. After this multi-stage processing, a residual image emerged from the August 2024 data. In that image, a point source appeared. It was designated the source, or S1. It appeared at a projected separation of approximately 1.94 arcseconds from Alpha Centauri A, corresponding to a physical projected separation of roughly 2.0 astronomical units at the system's distance. Its brightness at 15.5 micrometers was measured at a contrast ratio of approximately 10 to the negative 4 relative to Alpha Centauri A, 10,000 times fainter than the star. The team subjected S1 to an extensive battery of consistency checks. They examined whether the source position was consistent with a known background star or galaxy. Alpha Centauri's high proper motion, Approximately 3.7 arcseconds per year relative to background objects means that the system moves rapidly across the sky. Any background object at S1's position would have appeared at a different location relative to the stars in archival images taken years earlier. Cross-matching against archival data revealed no known background source at the position where S1 appeared. They checked whether S1's brightness and colour were consistent with a foreground solar system object such as an asteroid or Kuiper belt body drifting through the field during the observation. The expected thermal brightness of solar system objects at that angular position was inconsistent with the detected flux. They examined whether S1's position corresponded to a known artifact location in MIRI's focal plane, such as a detector persistence feature, a ghost from internal reflections, or a systematic bright spot in the flat field response. No such artifact was identified at the relevant position. The checks did not confirm S1 as a planet. They ruled out the simplest alternative explanations. What remained after the ruling out was a faint point source of uncertain nature, positioned in the habitable zone of Alpha Centauri A, with properties consistent in principle with a gas giant comparable in mass to Saturn, a Saturn in the habitable zone. If the source detected in Webb's August 2024 data is a planet, its physical properties can be estimated from the available photometric information. The team's analysis, published in 2 companion papers submitted to the Astrophysical Journal Letters, constructs a preliminary portrait of the candidate based on its brightness at 15.5 micrometers, its projected separation from Alpha Centauri A, and the constraints imposed by the orbital modelling described in the papers. The brightness of S1 at 15.5 micrometers corresponds under the assumption that it is a thermally emitting body rather than a reflected light source to an effective temperature of approximately 300 to 400 Kelvin. This temperature range is consistent with a gas giant that has retained some residual heat from its formation, supplemented by heating from the relatively luminous host star Alpha Centauri A at separations of 1 to 2 astronomical units. The total luminosity of Alpha Centauri A is approximately 1.5 times that of the Sun, which means that its habitable zone receives more flux per unit area than the equivalent zone around our Sun. A planet at 1.5 astronomical units from Alpha Centauri A receives roughly the same stellar flux as Earth does from our Sun. The thermal emission model that best fits the observed mid-infrared brightness yields a planet radius of approximately 0.9 to 1.0 Jupiter radii, corresponding to a mass range of roughly 90 to 150 Earth masses, or about 0.3 to 0.5 Jupiter masses. This places the candidate solidly in the Saturn mass regime. Saturn itself has 95 Earth masses and a radius close to 0.84 Jupiter radii. The candidate is somewhat larger and more massive than Saturn, but occupies the same planetary category: a gas giant, a massive envelope of hydrogen and helium with no solid surface, incapable of supporting life as we understand it. The orbital parameters derived from the single August 2024 detection, combined with the 2019 near detection of C1, constrain the candidate's orbit to an elliptical path with a semi-major axis of roughly 1.1 to 2.4 astronomical units, an eccentricity of approximately 0.3 to 0.5, and an orbital period of roughly 1.5 to 3.4 years. The orbit is significantly inclined relative to the orbital plane of the Alpha Centauri A and B binary system, with an inclination estimate of 50 to 130 degrees. This last parameter is unusual. Planets that form from protoplanetary disks should in general orbit in roughly the same plane as the disk, which itself tends to align with the binary orbital plane for systems where the binary formed from the same molecular cloud core. An inclination of 50 to 130 degrees relative to the binary plane implies either formation through an unusual mechanism, gravitational scattering by other bodies in the system after formation in a more typical configuration, or capture from a passing object. The orbital eccentricity of roughly 0.4 is also higher than what simple disk formation models predict for planets in binary systems. Theoretical studies of planet formation in tight binaries suggest that the gravitational perturbations from the companion star should either prevent planetesimal accumulation entirely at certain semi-major axes, or circularize the orbits of planets that do manage to form through dynamical friction from the residual disk material. A planet maintaining an eccentricity of 0.4 after billions of years of evolution in the Alpha Centauri binary suggests either that circularization has been incomplete, that the eccentricity is being maintained or excited by some additional dynamical mechanism, or that the planet arrived in its current orbit through a process other than in situ formation. What this candidate's location implies, regardless of its formation history, is that the habitable zone of the nearest Sun-like star is occupied, not by a rocky world with liquid water oceans, but by a gas giant in an eccentric orbit that sweeps through the habitable zone on a timescale of years. If confirmed, this would immediately raise the question of whether any smaller, potentially rocky planets share this system's inner orbital architecture. In our own solar system, Jupiter's presence affected the formation and orbital evolution of the terrestrial planets profoundly. Analogous interactions at Alpha Centauri A would have shaped whatever inner planetary system formed there. The gas giant, if real, is not just an isolated discovery. It is a constraint on the entire planetary architecture of the nearest Sun-like star. When the planet vanished, the detection of S1 in the August 2024 data was compelling enough to warrant immediate follow-up. In observational astronomy, a single epoch of data is not sufficient to establish the existence of a new object. A real planet follows a predictable orbit, moving relative to the host star in a manner consistent with Keplerian dynamics. A real planet should be detectable in follow-up observations, provided the instrument sensitivity is adequate and the planet has not moved into a region of its orbit where detection becomes geometrically impossible. The team secured additional Webb time through the director's discretionary program. 2 follow-up observations were executed, one in February 2025 and one in April 2025. Both used the same Miri coronagraphic configuration as the August 2024 observation. Both were processed through the same data reduction pipeline with the same reference star subtraction and Alpha Centauri B point spread function removal procedures. Both should have been sensitive to S1 if the candidate remained at approximately the same position and brightness as in the initial detection. S1 was not present in either follow-up observation. The February 2025 image showed no point source at the position where S1 had appeared 6 months earlier. The April 2025 image similarly returned no detection. The non-detections were not marginal, they were clean. The data quality in both follow-up windows was comparable to the August 2024 observation. The processing pipeline performed normally. The sensitivity limits derived from the noise floors of the 2 follow-up images were sufficient to detect an object at S1's August 2024 brightness if it had been located at its previous position. The straightforward interpretation of this pattern is that S1 was a spurious detection, a false positive that survived the August 2024 analysis by chance, or a transient astrophysical phenomenon with no connection to a stable orbiting planet. This interpretation is scientifically conservative, statistically defensible, and consistent with the baseline expectation that unconfirmed single epoch detections near bright stars are often noise. The team did not abandon the candidate on the basis of the non-detections, and their reason for not doing so rests on orbital mechanics rather than optimism. A planet on an elliptical orbit does not maintain a fixed angular separation from its host star. Its projected position on the sky, as seen from Earth, changes continuously as it moves around its orbit. At certain orbital phases, the planet may appear at large angular separations from the star, well outside the coronagraph's inner working angle and, in principle, detectable. At other phases, the planet may appear at small angular separations, falling inside the inner working angle where residual starlight from the coronagraph overwhelms any faint companion signal. At still other phases, the planet may be in front of or behind the star as projected onto the plane of the sky, even if it is not physically in conjunction with the star in 3 dimensions. The team ran computational simulations of the candidate's orbit. Starting from the constraints established by the August 2024 detection position and the 2019 C1 position, they generated a large ensemble of possible orbits consistent with both observed positions. For each simulated orbit, they calculated where the candidate would have been during the February 2025 and April 2025 observation windows. They then asked whether the projected separation during those windows would have fallen inside Miri's inner working angle, making the candidate undetectable regardless of its physical presence. The result was that in approximately 52% of the stable orbital solutions consistent with the detection data, the candidate's projected separation from Alpha Centauri A during both the February and April windows fell inside the coronagraph's inner working angle. In more than half of the plausible orbital solutions, the candidate would have been undetectable during both follow-up observations, even if it had been sitting exactly where the models predicted. The non-detections were consistent with, and in fact expected under, a significant fraction of the real planet hypothesis space. This analysis does not confirm the planet. It prevents the non-detections from falsifying the hypothesis. Those are different conclusions, and the distinction is important. The team's position is not that the planet is real. It is that the existing data, including both the detections and the non-detections, are consistent with a real planet on a plausible orbit. The candidate survives. The case for it has not strengthened, but it has not been eliminated. The next test will come from a predicted redetection window. The team's orbital models indicate that if the candidate is real, the geometry of its orbit should carry it back to a projected position outside Miri's inner working angle sometime in the second half of 2026, most likely around August. If Webb observes Alpha Centauri A again during that window and S1 reappears at the predicted location with the predicted brightness, the case for a real planet will be extremely strong. A detection at a predicted position and brightness, derived from a model built on 2 independent detections separated by 5 years, would be essentially conclusive. If S1 does not reappear in 2026, the hypothesis weakens substantially. Some orbital configurations could still explain a further non-detection, but the cumulative weight of 1 appearance and 3 non-detections would challenge the planetary interpretation severely. The 2019 detection nobody remembered. Before Webb turned its eye toward Alpha Centauri A in 2024, there was a prior observation that most coverage of the discovery has underweighted. It occurred in 2019. It used entirely different technology, and its results were cautiously published in 2021 with a hedged conclusion that planted an unanswered question in the literature for 5 years. Understanding it properly changes how the Webb detection is interpreted, because the 2024 observation did not occur in isolation. It occurred against the background of an earlier ambiguous signal from the same star. The instrument used in 2019 was called NEAR, an acronym standing for New Earths in the Alpha Centauri region. It was a thermal infrared coronagraphic imager installed on Unit Telescope 4 of the Very Large Telescope at the European Southern Observatory's Paranal facility in the Atacama Desert of Chile. NEAR was not a general-purpose instrument. It was built for exactly one scientific mission: to search for planets in the habitable zones of Alpha Centauri A and B. The instrument was developed through a collaboration between the European Southern Observatory and Breakthrough Watch, the observational branch of the Breakthrough Initiatives program, founded by Russian-Israeli investor Yuri Milner in 2015. with the explicit goal of advancing the search for extraterrestrial intelligence and habitable worlds around nearby stars. NEAR operated at mid-infrared wavelengths between approximately 10 and 12.5 micrometers, a range chosen for the same reason Webb's MIRI team chose 15.5 micrometers. The contrast between a Sun-like star and a warm planetary companion is far more favourable in the thermal infrared than in visible light. The instrument incorporated a vector vortex coronagraph optimised for the relevant angular separations and a deformable mirror to correct residual wavefront errors introduced by the Earth's atmosphere. At the time of its commissioning in 2019, NEAR represented the most sensitive ground-based instrument ever built specifically for direct imaging of planets around Alpha Centauri. The observing campaign ran for approximately 100 hours in May and June of 2019. This was an extraordinary investment of time on one of the world's most oversubscribed telescopes. The team, led by Kevin Wagner at the University of Arizona's Stewart Observatory, along with collaborators including Marcus Casper of ESO and Olivier Abseil of the University of Liège, conducted a deep coronagraphic survey of the region surrounding Alpha Centauri A and B. After processing the data through their pipeline, which included reference star subtraction and speckle suppression algorithms, a faint source appeared in the residual images near Alpha Centauri A. The source, designated C1, appeared at a projected angular separation of approximately 0.84 arcseconds from Alpha Centauri A, corresponding to a projected physical separation of roughly 1.1 astronomical units. At the 10 to 12.5 micrometer wavelengths where NEAR operated, the source had a flux density consistent with a thermal emitter at a temperature of several hundred Kelvin and a size somewhere in the range of Neptune to Saturn. The team examined the data carefully. They could not rule out the possibility that C1 was an artifact of the instrument's speckle pattern, a persistent, coherent noise feature that mimics the appearance of a point source in coronagraphic images. They could not rule out the possibility that it was a compact clump of warm exozodiacal dust in orbit around the star rather than a solid or gaseous planet. The observational arc covered by the 100-hour campaign was not long enough to detect orbital motion of C1 relative to Alpha Centauri A, which meant they could not confirm that the source was gravitationally bound to the system. The team published their results in Nature Communications in 2021 under the title Imaging Low-Mass Planets Within the Habitable Zone of Alpha Centauri. The paper described C1 as a candidate that required follow-up observations at different wavelengths and epochs to characterize fully. The community's response was measured. The result was interesting, but not conclusive. No independent team confirmed C1 with a different instrument. No follow-up observations with NEAR or other facilities produced a second detection at the same location. CE1 entered the literature in the category reserved for tantalizing but unconfirmed astrophysical hints. What gave the 2024 Webb detection its extra layer of significance was the decision by the Webb team to test whether S1 and C1 might be the same object. The two detections were made 5 years apart by instruments operating at different wavelengths, from different platforms, with different coronagraphic technologies. S1 appeared at a projected separation of approximately 2.0 astronomical units from Alpha Centauri A in August 2024. C1 appeared at a projected separation of approximately 1.1 astronomical units from Alpha Centauri A in 2019. If these 2 points represent the same object at two different points in its orbit, the object must have moved from a projected distance of 1.1 astronomical units to a projected distance of 2.0 astronomical units between 2019 and 2024, while also changing its orientation relative to the star. The team constructed orbital models that attempted to fit both detections simultaneously, along with the two non-detections in February and April 2025. They generated an ensemble of test orbits, each consistent with the positional constraints from both C1 and S1, and then asked which orbits could also explain why the source was not detected in the two follow-up windows. The analysis yielded a family of orbital solutions with semi-major axes between roughly 1.1 and 2.4 astronomical units, eccentricities centered around 0.4 comma orbital periods of approximately 1.5 to 3.4 years, and inclinations of 50 to 130 degrees relative to the binary plane. These are not the same numbers as a simple fit to either detection alone would produce. They are the combined solution that accounts for all four data points simultaneously. Two inconclusive single-epoch detections from two separate observatories, 5 years apart, with two follow-up non-detections explained by orbital geometry. None of these four data points constitutes a discovery individually. Together, they trace the outline of something that may be orbiting the nearest Sun-like star. The fact that this outline requires a specific mass range, a specific eccentricity range, and a specific inclination range to be self-consistent transforms a collection of ambiguous data points into a quantitative hypothesis. That hypothesis will be tested in 2026, but its roots extend back not to August 2024, when Webb first observed, but to a 100-hour campaign in the Chilean desert 5 years earlier that most of the world has already forgotten. The orbital models. Planetary orbital mechanics is not an exercise in hypothesis preservation. When a team of astronomers generates millions of simulated planetary orbits and filters them for consistency with available observations, they are applying strict physical constraints to a mathematical problem with a large solution space. The result is not a narrative argument for a desired conclusion. It is a quantitative characterization of which parts of parameter space are consistent with the data and which are not. The orbital modelling that kept the Alpha Centauri candidate alive after two non-detections deserves careful examination, because it is where the science becomes most rigorous and most illuminating. The foundational input to the modelling is the set of detected positions. C1 in 2019 appeared at a projected separation of approximately 1.1 astronomical units from Alpha Centauri A at a position angle of roughly 110 degrees east of north. S1 in August 2024 appeared at a projected separation of approximately 2.0 astronomical units at a position angle of roughly 170 degrees east of north. These two coordinates in the projected plane of the sky, separated by approximately 5.2 years, are the anchor points around which the orbital solutions must be constructed. A single detected position constrains an orbit very loosely. If you know where a planet is at one moment, you cannot determine its orbit without also knowing its velocity at that moment. The projected position gives you two numbers, an angular separation and a position angle. The velocity is unknown. An infinite family of orbits passes through any single point in space, ranging from nearly circular paths to highly eccentric ones, from prograde to retrograde, from low inclination to nearly polar. The set of possible orbits is enormous. Adding a second detected position dramatically narrows the solution space. If the planet was at position C1 in 2019 and at position S1 in 2024, then it moved from one location to the other over approximately 5.2 years. This movement must be consistent with gravitational orbit, a path obeying Kepler's laws around Alpha Centauri A as the dominant gravitational attractor. The time baseline between detections constrains how fast the planet was moving, which in turn constrains the orbital semi-major axis through Kepler's third law. The angular displacement constrains the orbital geometry. The combination of the two positions and the time baseline between them reduces the family of consistent orbits from infinite to a manageable, though still large, ensemble. The team then applied an additional constraint from the system's dynamical environment. Alpha Centauri A does not sit alone. It has a binary companion, Alpha Centauri B, currently separated by approximately 21.5 astronomical units as of mid-2024. The gravitational influence of Alpha Centauri B destabilizes planetary orbits around Alpha Centauri A that extend beyond a certain semi-major axis. Numerical integration studies of test particle stability in the Alpha Centauri binary system, including those by Qualls and Lissauer, published in 2016 in the Astrophysical Journal, established that planets can survive on stable orbits around Alpha Centauri A, out to approximately 3 astronomical units for low inclination prograde orbits, with the stability boundary shrinking for higher eccentricities and inclinations. Orbits that extend significantly beyond this stability limit are eventually ejected from the system on timescales short compared to the stellar age. The team applied dynamical stability filtering to their ensemble of test orbits. Orbits whose semi-major axes and eccentricities combined to take the candidate planet into the dynamically unstable zone around Alpha Centauri A were excluded. This filtering further reduced the viable solution space and concentrated the surviving orbitae in a specific region of parameter space, semi-major axes of 1 to 2.5 astronomical units, eccentricities of 0.2 to 0.6, inclinations spread broadly, but with some preference for inclinations between 50 and 130 degrees, where the combination of projected positions and time baseline is most easily satisfied. With this filtered ensemble of dynamically viable orbits in hand, the team then asked the question that connects the orbital modelling to the non-detections. For each surviving test orbit, what would be the candidate's projected position during the February 2025 observation window and the April 2025 observation window? Would those positions fall inside or outside Miri's inner working angle of approximately 0.33 arcseconds, corresponding to a projected physical separation of roughly 0.44 astronomical units at Alpha Centauri's distance? The inner working angle is not a smooth boundary. It is defined by the coronagraph's suppression performance as a function of angular separation. Inside the inner working angle, the residual stellar speckle brightness exceeds the planet's signal and detection becomes impossible. The boundary is somewhat wavelength dependent and depends on how well the star was centered on the mask during the observation. But the general criterion is that any planet appearing at a projected separation below about 0.44 astronomical units in the sky plane would be undetectable regardless of the instrument's sensitivity to sources at larger separations. Many of the candidate's possible orbits, particularly those with higher eccentricities and certain inclination combinations, naturally produce phases where the projected separation from Alpha Centauri A drops below this threshold. A planet on a significantly elliptical orbit can be at a large true physical distance from its star while simultaneously appearing at a small projected angular separation, if the component of its orbital position along the line of sight from Earth is large. The geometry of a tilted eccentric orbit creates exactly this situation for specific combinations of orbital phase and orbital orientation. The 52% figure that the team derived refers to the fraction of the dynamically stable orbital solutions consistent with both detections in which the candidate's projected separation fell below the inner working angle during both the February and April 2025 windows. More than half of the viable orbits naturally predict non-detection in those windows. This fraction is high enough to prevent the non-detections from falsifying the planetary hypothesis under a straightforward statistical treatment. The same modelling makes a prediction for 2026. Across the ensemble of surviving orbital solutions, the candidate's projected separation grows back outside the inner working angle sometime during the northern summer of 2026 for a majority of the viable orbits. The optimal window, according to the team's calculations, falls around August 2026, close to the anniversary of the original detection. The prediction is specific enough to be testable. If Webb observes Alpha Centauri A during that window and detects a source at the brightness and position angle predicted by the orbital ensemble, the planetary interpretation becomes very difficult to dismiss. A random artifact does not follow orbital predictions derived from detections made 5 and 10 years earlier. What the candidate actually is. The detection papers submitted to the Astrophysical Journal. Letters by Carter, Beichmann, Panu, and their co-authors are careful documents. They do not claim a planet. They present a candidate, characterize its properties under several interpretive frameworks, and explicitly enumerate the alternative explanations that remain viable. This kind of epistemic discipline is standard practice in high-stakes astrophysics, but it is also frustrating for anyone who wants a clean answer. The candidate is real in the sense that the signal is in the data. What the signal represents is the open question, and understanding the full range of possibilities is essential to appreciating what the 2026 reobservation will actually resolve. The most favoured interpretation is a gas giant with a mass somewhere between 90 and 150 Earth masses, placing it in the Saturn to sub-Jupiter range. At 15.5 micrometers, the mid-infrared channel that MIRI used for this observation, thermal emission from the planet's atmosphere is the dominant source of detectable flux. A body of this mass at a separation of roughly 1 to 2 astronomical units from Alpha Centauri A would have retained significant internal heat from its formation and would also be receiving a substantial flux of stellar radiation, enough to maintain an atmospheric temperature of several hundred Kelvin. The combination of residual formation heat and stellar irradiation produces a mid-infrared luminosity that is detectable by MIRI at the observed contrast ratio, provided the coronagraphic suppression and reference star subtraction have performed adequately. The brightness of S1 at 15.5 micrometers is consistent with an object radius close to 1 Jupiter radius. This is somewhat larger than Saturn, which has a radius of 0.843 Jupiter radii, but Saturn-class gas giants span a range of radii depending on their age, composition, and irradiation history. A gas giant in the mass range of 90 to 150 Earth masses that form from a solar composition protoplanetary disk cooled over a stellar age of approximately 5 to 6 billion years and has been irradiated at a level comparable to Earth's insolation, would be expected to have a radius and effective temperature broadly consistent with what was observed. The thermal evolution models of giant planets, developed by researchers including Jonathan Fortney at the University of California, Santa Cruz, and Adam Burrows at Princeton University, predict atmospheric temperatures in the 200 to 400 Kelvin range for such an object, with mid-infrared fluxes that place the detection at approximately the level observed. The second viable interpretation is warm exozodiacal dust. Every mature planetary system is expected to contain some population of fine dust particles generated by collisions among asteroids and by the evaporation of comets as they approach the host star. In our own solar system, this zodiacal dust is distributed in a diffuse disk concentrated near the ecliptic plane. It has been detected by spacecraft including Helios, and its infrared emission contributes a faint glow visible from Earth as the zodiacal light, a cone of illumination seen along the ecliptic after evening twilight and before morning twilight. Around other stars, analogous structures are called exozodiacal dust, and their detection has become a significant branch of infrared astronomy. Warm exozodiacal dust around Alpha Centauri A would orbit within a few astronomical units of the star, heated by stellar radiation to temperatures of several hundred Kelvin. At those temperatures, the dust emits thermally in the mid-infrared at exactly the wavelengths where MIRI was observing. If the dust is distributed in a clump, perhaps concentrated by the gravitational influence of an unseen planet or temporarily enhanced by a recent collision event, it could appear as a compact bright source in the coronagraphic image. The key distinction between dust and a planet is dynamical behaviour. Dust redistributes along its orbit on timescales governed by the Poynting-Robertson effect and collisional lifetimes, and a clump is not expected to persist at the same orbital location for years. A planet follows a strictly Keplerian orbit and reappears at predictable positions. If S1 reappears in August 2026 at the position predicted by the orbital models derived from the combined C1 and S1 detections, the dust hypothesis effectively collapses. Dust does not obey orbital mechanics derived from planetary mass assumptions. The team used the August 2024 data to place upper limits on the total exozodiacal dust luminosity around Alpha Centauri A. Their analysis constrained the dust level to no more than a few hundred times the density of our own solar system's zodiacal cloud, expressed as a fractional luminosity relative to the host star. This upper limit is itself a scientifically valuable result, but it does not eliminate dust as an explanation for S1 specifically. A moderately concentrated clump of dust within an otherwise modest zodiacal disk could produce the observed point source signal without violating the global upper limit. The constraint rules out a thick, uniform dust disk, not a localized enhancement. A third possibility that the team evaluated is an unresolved background galaxy. Compact galaxies at cosmological distances can appear as point sources in infrared images. However, the positional cross-matching against archival catalogues found no known background source at S1's location, and the expected number density of galaxies bright enough to produce S1's observed flux at 15.5 micrometers is low enough that a chance alignment of this magnitude would be statistically unlikely. This explanation was assessed as the least probable of the alternatives. The team did not eliminate it entirely, since a sufficiently faint or unusual background object might not appear in existing catalogues, but its statistical weight is small compared to the planetary and dust interpretations. The distinction between these three interpretations cannot be resolved from the August 2024 data alone. It requires either the redetection of S1 at a predicted location, confirming orbital motion consistent with a bound planet, or the detection of S1 at multiple wavelengths simultaneously, which would constrain the spectral energy distribution and allow the thermal emission properties of the source to distinguish between a gaseous atmosphere and a distribution of small dust grains. Both of these approaches require additional observing time. Both require Webb to look again, and neither will be possible until the 2026 observation window opens. A fourth possibility, less discussed but worth registering, is that S1 is an unresolved stellar companion, a very low-mass star or brown dwarf on a wide orbit around Alpha Centauri A, that was not detected by prior surveys because it fell within the glare of the primary. Brown dwarfs, with effective temperatures of a few hundred Kelvin, emit strongly in the mid-infrared and could produce a contrast ratio consistent with S1's observed brightness. However, a brown dwarf massive enough to remain thermally luminous enough to be detectable at these wavelengths after several billion years of cooling would typically retain a mass above roughly 13 Jupiter masses, approximately 4,100 Earth masses. An object of this mass on an orbit at 1 to 2 astronomical units from Alpha Centauri A would induce a radial velocity signal in the host star of several hundred meters per second, far above the noise floor of the HARPS and espresso monitoring campaigns that have been conducted over years of observation. The absence of any such signal in published radial velocity datasets is strong evidence against the brown dwarf interpretation. The team addresses this point directly in the discovery papers and considers the brown dwarf hypothesis effectively ruled out by the prior radial velocity constraints. What the comparison of these four scenarios illustrates is that the observational evidence currently in hand is sufficient to eliminate some classes of explanation, but insufficient to discriminate between the remaining viable ones. This is the standard condition of early-stage planet candidate science. A single detection epoch combined with two non-detections provides a strong prior in favour of some classes of orbit and some classes of source, but it cannot uniquely determine the nature of the signal without additional constraints. The resolution pathway is both clear and time-consuming. Additional detection epochs multi-wavelength photometry, and eventually spectroscopy if the planetary interpretation survives the upcoming observational tests. The candidate will be confirmed or dismissed by data collected in the coming years, not by any further analysis of what already exists. Why a binary makes planets hard. The question of whether planets can form and survive around either star in the Alpha Centauri binary is not settled by observation alone. It is also a theoretical question that has occupied planetary scientists for decades, and the answers that theory provides are more nuanced and more contested than popular accounts suggest. Planet formation begins with the protoplanetary disk, the rotating flattened structure of gas and dust that surrounds a young star in the first few million years of its existence. Within the disk, microscopic dust grains collide and stick together, gradually building up progressively larger bodies through a process called coagulation. Over millions of years, these bodies grow from dust to pebbles, to planetesimals, to planetary embryos, to, eventually, full planets. The process is well understood in outline for isolated single stars, where the disk extends outward in an unperturbed fashion until stellar winds and radiation eventually disperse it. In a binary star system, the disk does not extend unperturbed. The gravitational influence of the companion star truncates the disk at an outer boundary determined by the binary's orbital parameters. For Alpha Centauri A and B, with their current orbital separation ranging from 11.2 to 35.6 astronomical units, and their mass ratio of approximately 1.1 to 0.9 solar masses, the truncation radius for a disk around Alpha Centauri A is estimated at approximately 2 to 4 astronomical units, depending on the disk viscosity, the binary's eccentricity, and the specific dynamical resonances that are excited. Simulations by Artymovits and Lyubov in 1994, published in the Astrophysical Journal, established the foundational framework for disk truncation in binary systems, and subsequent numerical studies have refined these estimates for the specific parameters of the Alpha Centauri pair. The truncation of the disk has several consequences for planet formation. First, it limits the total reservoir of solid material from which planets can assemble around each star. A disk truncated at 3 astronomical units contains less total mass than a disk extending to 30 or 100 astronomical units, assuming similar surface density profiles. Second, it creates a dynamic boundary at the disk's outer edge, where particles experience periodic gravitational perturbations from the companion star. These perturbations pump up the eccentricities and inclinations of planetesimals near the outer disk boundary, increasing the relative velocities at which they collide. High-velocity collisions between planetesimals are erosive rather than accretive. Instead of sticking together to build larger bodies, planetesimals shatter into fragments, impeding rather than advancing planetary growth. This erosion problem was explored in detail by Thibault, Marzari and Scholl in a series of papers published between 2006 and 2009. Their simulations showed that for the specific orbital configuration of Alpha Centauri A and B, the companion star's gravitational forcing raises planetesimal collision velocities to values high enough to prevent efficient accretion in the outer disk, with the problematic zone extending from roughly 0.5 astronomical units outward. In the inner disk, closer to Alpha Centauri A, the companion's influence is reduced and accretion can proceed more normally. Their models suggested that rocky planets could form within about 1 astronomical unit of Alpha Centauri A, but that planet formation becomes increasingly difficult at larger separations. More recent work has revised this picture somewhat. Studies by Parda-Cooper and colleagues and by Z and collaborators showed that the aerodynamic gas drag in the early protoplanetary disk can reduce the effective eccentricity dispersion among planetesimals in the presence of binary perturbations, allowing accretion to proceed more efficiently than the purely gravitational simulations suggested. The presence of gas in the disk during the first few million years damps planetesimal orbits, suppressing the binary-induced eccentricity excitation and creating a more favourable environment for accretion. In these models, planet formation is possible out to somewhat larger separations than earlier work predicted, with the exact limits dependent on the binary's orbital parameters and the disk's gas-to-dust ratio and lifetime. The theoretical situation as of 2025 is therefore this: planet formation around Alpha Centauri A within approximately 1 to 2 astronomical units is plausible and possibly efficient, consistent with what works for isolated stars. Planet formation between 2 and 3 astronomical units is marginally possible depending on disk conditions. Planet formation beyond 3 astronomical units is difficult to impossible for most plausible disk models. A Saturn mass gas giant at 1 to 2 astronomical units sits in the range where formation is theoretically permissible but not guaranteed, and its specific orbital properties, particularly its eccentricity of roughly 0.4 and inclination of 50 to 130 degrees relative to the binary plane, suggest a formation or dynamical history that straightforward in situ accretion cannot easily explain. Gas giant formation specifically, as opposed to rocky planet formation, adds another layer of complexity. The leading theory for gas giant formation is core accretion. A rocky or icy core of roughly 5 to 15 Earth masses assembles first through solid body accretion and then triggers rapid accretion of gas from the surrounding disk once the core becomes massive enough to gravitationally attract and retain a substantial gaseous envelope. This process takes time, typically several million years for a Jupiter-class planet at several astronomical units, and it requires the disk to retain its gas reservoir long enough for runaway accretion to complete. If the binary companion truncates or depletes the disk more rapidly than would occur for an isolated star, there may be insufficient time for a gas giant core to trigger runaway gas accretion before the disk dissipates. Alternative formation pathways exist. Gravitational instability, a mechanism in which a sufficiently massive and cold disk fragments directly into gas giant progenitors without needing a pre-existing solid core, could in principle form a giant planet rapidly, on timescales of thousands rather than millions of years. But gravitational instability typically operates at large disk radii, beyond 50 or 100 astronomical units, far outside the truncated disk that surrounds Alpha Centauri A. Applying it to produce a giant planet at 1 to 2 astronomical units requires invoking subsequent inward migration, which brings its own set of dynamical complications. The bottom line from planetary formation theory is that a Saturn mass planet at 1 to 2 astronomical units from Alpha Centauri A is possible within the current state of the models, but its orbital properties, particularly its eccentricity and inclination, are difficult to explain as the product of simple in situ formation. If the candidate is confirmed, theorists will need to develop explanations for how it achieved its current orbit, whether through scattering by other planets, secular perturbations from Alpha Centauri B, disk-planet interactions in an inclined disk, or some combination of these mechanisms. Each explanation carries different implications for what else might be present in the system. The stability boundary. Even if a planet forms successfully around Alpha Centauri A, its long-term survival is not guaranteed. The gravitational environment created by the Alpha Centauri A and B binary is dynamic and time-varying, and its effect on planetary orbits extends well beyond the initial formation epoch. Understanding where a planet can survive for billions of years in this system is a precise dynamical question with quantitative answers, and those answers define the observable space within which any confirmed planet must sit. The key concept is the Hill stability boundary, which describes the maximum orbital radius at which a planet around one component of a binary can remain bound to that component rather than being transferred to a circumbinary orbit or ejected from the system entirely. For a binary with the parameters of Alpha Centauri A and B, the Hill stability boundary around each star is roughly 1/3 of the binary's periastron separation. With a periastron distance of approximately 11.2 astronomical units for the Alpha Centauri binary, this criterion places the stability boundary around Alpha Centauri A at roughly 3 to 4 astronomical units for circular orbits. Eccentric planetary orbits reduce the effective stability limit. A planet on an orbit with eccentricity 0.4, reaching out to an apastron of 2.4 astronomical units, while its semi-major axis is 1.7 astronomical units, spends portions of its orbit closer to the stability boundary than a circular orbit at the same semi-major axis would. Numerical integration studies specifically targeting the Alpha Centauri system, including the work by Quarles and Lissauer published in 2016 in the Astrophysical Journal, and subsequent studies incorporating more detailed binary orbital parameters, show that prograde, low-inclination orbits around Alpha Centauri A remain stable out to roughly 3 astronomical units for low eccentricity cases, with the boundary shrinking to approximately 2 astronomical units for orbital eccentricities around 0.4. Retrograde orbits, in which the planet orbits in the opposite sense to the binary's orbital motion, can be stable at slightly larger radii due to the averaging of gravitational perturbations over the retrograde orbit. Highly inclined orbits are subject to a qualitatively different dynamical mechanism, the Kozai-Lidov effect, named after Yoshihide Kozai and Michael Lidov, who independently described it in 1962. Under this effect, a companion on an inclined orbit relative to a test particle's orbital plane drives coupled oscillations in the test particle's eccentricity and inclination on timescales long compared to its orbital period. For a planet inclined at 50 to 130 degrees relative to the binary orbital plane, as the candidate's orbital solution suggests, the Kozai-Lidov mechanism could drive periodic excursions to high eccentricity, potentially carrying the planet's orbit to apastron distances that temporarily approach or exceed the stability boundary. Whether the Kozai-Lidov mechanism is actively operating on the candidate's orbit and at what amplitude depends on the specific inclination and the timescale of the oscillation cycle relative to the system age. For inclinations near 90 degrees, the Kozai-Lidov timescale for a planet at 1 to 2 astronomical units in the Alpha Centauri binary can be on the order of tens of thousands to hundreds of thousands of years. General relativistic precession of the planet's orbit, which is non-negligible for objects at these separations, tends to suppress the Kozai-Lidov oscillations by introducing an additional precession timescale that can quench the eccentricity pumping. The balance between these effects determines whether the candidate's orbit is currently evolving rapidly or is in a quasi-stable configuration where the Kozai-Lidov amplitude is suppressed. This dynamical complexity is not merely academic. If the candidate planet is on a Kozai-Lidov active orbit, its eccentricity and inclination are not constant. They oscillate on a known timescale, and the current values we infer from the orbital model represent a snapshot of the oscillation rather than a permanent state. At the minimum eccentricity phase of the Kozai-Lidov cycle, the planet could be on a nearly circular orbit well inside the stability boundary. At the maximum eccentricity phase, it could swing to apastron distances approaching 3 or 4 astronomical units, nearly reaching the stability limit, before the eccentricity drops back down. The system would be dynamically complex, but not necessarily unstable over billions of years. Understanding which dynamical regime the candidate occupies requires knowing its inclination, eccentricity, and orbital orientation with a precision that the current sparse detection dataset cannot provide. A confirmed redetection in 2026, combined with orbital monitoring over several full orbital periods, would gradually resolve these questions. But for now, the candidate's orbital properties exist in a space that is consistent with long-term stability for a range of dynamical scenarios while also being consistent with active dynamical evolution for others. what remains invisible. One of the most consequential aspects of the Webb observation is what it could not detect and what the inability to detect it implies about the completeness of our current knowledge of the nearest Sun-like stellar system. MIRI's coronagraphic observation at 15.5 micrometers was sensitive to objects above a certain brightness threshold, corresponding to a contrast ratio of roughly 10 to the -4 relative to Alpha Centauri A at angular separations beyond the inner working angle of about 0.33 arcseconds. At Alpha Centauri's distance, this inner working angle translates to a physical projected separation of roughly 0.44 astronomical units. Everything inside that radius and everything outside it but fainter than the detection threshold is invisible to this observation. The brightest class of planets detectable under these conditions is warm gas giants. Worlds in the Saturn to Jupiter mass range with effective temperatures of 200 to 500 Kelvin, whose mid-infrared thermal emission is strong enough to rise above the noise floor created by the residual stellar speckle pattern. The candidate S1 sits at or near the faint end of this detectable range. A gas giant significantly cooler than S1, or one in a mass range below roughly 50 to 70 Earth masses, would fall below the detection threshold and would not have appeared in the data even if it were present. Neptune-sized planets are invisible to this observation. Neptune has a mass of approximately 17 Earth masses and a radius of roughly 0.35 Jupiter radii. At temperatures consistent with irradiation by Alpha Centauri A at separations of 1 to 2 astronomical units, a Neptune-class world would emit roughly 10 to 20 times less mid-infrared flux than the candidate S1. That places a Neptune-sized planet at least an order of magnitude below the contrast ratio that MIRI achieved with this observation. It is not a marginal non-detection, it is a complete non-detection. A Neptune in the habitable zone of Alpha Centauri A would not have left any signal above the noise floor, even in the cleanest part of the subtracted image. Super-Earths, defined as rocky or gaseous worlds with masses between 1 and 10 Earth masses, are several orders of magnitude fainter still. The mid-infrared thermal emission from a super-Earth in the habitable zone is determined by its equilibrium temperature and radius. For a planet with a radius twice that of Earth at an irradiation level similar to Earth's, the emitted flux at 15.5 micrometers falls at a contrast ratio of roughly 10 to the -7 relative to Alpha Centauri A. The current observation achieved a contrast floor of approximately 10 to the -4. A super-Earth is 3 orders of magnitude too faint to detect with this observation. It is not merely beyond the current detection limit, it is orders of magnitude beyond it. This sensitivity boundary has profound implications for how we interpret the current state of knowledge about Alpha Centauri A. The observation detected one candidate object consistent with a Saturn mass gas giant. It places upper limits on the existence of similarly bright or brighter objects at separations outside the inner working angle, but it says absolutely nothing about the presence or absence of smaller planets. Alpha Centauri A could host an entire system of rocky planets in its inner habitable zone, planets resembling Earth or Mars or Venus, and the August 2024 Webb observation would not have detected any of them. They would all be invisible, not because they are absent, but because the instrument is not sensitive enough to see them at this wavelength. To make this concrete, consider what an astronomer at Alpha Centauri would observe if they used a telescope equivalent to Webb to examine our own solar system from 4.37 light-years away. Jupiter, with a mass of roughly 318 Earth masses and a radius of 1 Jupiter radius, would be a detectable thermal source in the mid-infrared. It would appear at an angular separation of approximately 1.2 arcseconds from the Sun, well outside the inner working angle, and its effective temperature of roughly 125. Kelvin would produce a mid-infrared flux at a contrast ratio of a few times 10 to the -5 relative to the Sun. That is near but not far above the detection threshold. Saturn, at 95 Earth masses and an effective temperature of about 95 Kelvin, would be a marginal detection at best. Everything else in our solar system, Uranus, Neptune, all 4 terrestrial planets, all asteroids, all comets, would be completely invisible. An Alpha Centauri astronomer observing our Sun with Webb-level technology would at most detect Jupiter and possibly Saturn. They would have no knowledge of Earth, no knowledge of Mars, no knowledge of Venus or Mercury, no evidence for any of the worlds that are relevant to the question of whether our solar system harbours a biosphere. This is the exact situation we are in when observing Alpha Centauri A. We are that Alpha Centauri astronomer, squinting at the nearest sun-like star with the best infrared telescope ever built, capable of seeing only the most massive and thermally luminous members of whatever family of planets might orbit there. The worlds that matter most for the question of habitability, the rocky planets with surfaces and atmospheres and liquid water potential, lie entirely below our current detection horizon. Whether they exist around Alpha Centauri A is a question that Webb, for all its extraordinary capability, cannot yet answer. The recorded would shatter. Placing the Alpha Centauri candidate in the context of the broader direct imaging exoplanet catalogue clarifies how anomalous it would be if confirmed, and why the astronomical community has responded to an ambiguous, unconfirmed result with such sustained attention. Direct imaging of exoplanets is among the most difficult techniques in observational astronomy. Of the approximately 6,000 confirmed exoplanets catalogued as of mid-2025, fewer than 80 have been directly imaged, representing less than 2% of the total. And the directly imaged planets that do exist share a distinctive set of properties that are far from representative of the general exoplanet population. They are almost universally young, massive, and widely separated from their host stars. The reason for this selection bias is straightforward. Young planets are hot. Gas giants formed within the last few tens of millions of years retain substantial heat from their formation and radiate strongly in the near-infrared and mid-infrared. As they age and cool, their thermal emission drops, making them progressively harder to detect. A 5-million-year-old gas giant may have an effective temperature of over 2000 Kelvin, glowing brilliantly in the near-infrared. The same planet at 5 billion years old would have cooled to perhaps 100 to 200 Kelvin, several orders of magnitude less luminous. Current direct imaging surveys preferentially target young stellar associations precisely because they contain young, thermally bright planets. Massive planets are also preferentially detected because they retain more formation heat and remain thermally luminous for longer. A 5 Jupiter mass planet cools much more slowly than a Saturn mass planet of the same age. The directly imaged planets in the HR 8799 system, discovered in 2008 by Marois and colleagues using the Keck and Gemini telescopes, have masses of approximately 5 to 7 Jupiter masses each. Beta Pictoris b, discovered in 2008 and confirmed in 2010, has a mass of approximately 9 to 13 Jupiter masses. 51 Eridani b, one of the cooler and more recently imaged examples, has a mass of approximately 2 Jupiter masses. These are not ordinary gas giants. They are massive superjupiters detectable because their youth and mass combine to produce thermal emission far above what older lower mass planets would emit. Widely separated planets are also overrepresented in the direct imaging catalogue because coronagraphs have an inner working angle below which starlight suppression fails. Planets at tens or hundreds of astronomical units from their host stars subtend large angular separations easily resolved by coronographic systems. The directly imaged planets in the HR 8799 system orbit at 14.5, 2438 and 68 astronomical units. Beta Pictoris b orbits at approximately 9 astronomical units at its closest approach. These are not the warm inner system planets where life might exist. they are cold giants in the outer reaches of their systems, detectable only because distance, rather than brightness, makes them accessible. The candidate at Alpha Centauri A would violate every one of these selection biases simultaneously. It would be old. The Alpha Centauri system is approximately 5.3 to 6.8 billion years old, comparable in age to our own solar system. Saturn itself, our best analogue for the candidate in terms of mass, formed roughly 4.5 billion years ago, and has spent those billions of years cooling to its present effective temperature of 95 Kelvin. The candidate, at a somewhat higher irradiation level, might maintain a slightly higher effective temperature, but it would still be orders of magnitude cooler than the young super-Jupiters that populate the current direct imaging catalogue. It would be low mass. At 90 to 150 Earth masses, it sits in the Saturn mass range. Every other directly imaged planet for which mass estimates are available is at least twice as massive, and most are 5 to 10 times more massive. Detecting a Saturn-class world at these ages and this mass range would require sensitivity that no previous direct imaging instrument has demonstrated. It would be close to its host star. An orbital separation of 1 to 2 astronomical units places it inside or near the habitable zone, far closer than the tens to hundreds of astronomical units where current direct imaging discoveries cluster. The angular separation of roughly 1 to 2 arcseconds corresponding to this physical separation is small enough that it falls within or near the inner working angle of most coronagraphic systems at visible wavelengths, requiring the mid-infrared advantage that MIRI provides, and it would be the nearest directly imaged exoplanet to Earth by a factor of roughly 10 to 20, depending on how distances to the systems hosting other directly imaged planets are compared. Alpha Centauri sits at 1.34 parsecs. The nearest other systems with directly imaged planet candidates are at distances of 10 to 20 parsecs. The contrast with the existing catalogue becomes starker when individual systems are examined directly. The HR 8799 system, which hosts 4 directly imaged planets designated B, C, D, and E, with masses ranging from 5 to 7 Jupiter masses each, sits at a distance of approximately 39 parsecs, roughly 129 light-years. Beta Pictoris, hosting the most famous directly imaged planet prior to the recent generation of discoveries, lies at 19.3 parsecs. 51 Eridani, whose planet 51 Eridani b is one of the cooler and lower mass directly imaged planets at roughly 2 Jupiter masses, sits at 29.8 parsecs. AF Leporis, whose planet at approximately 3 Jupiter masses was reported in 2023 using Gemini Planet Imager data, sits at 26.8 parsecs. Even the nearest directly imaged planet in the current catalogue, GQ Lupi b, at a distance of roughly 140 parsecs from Earth, is more than 100 times farther away than Alpha Centauri. Every one of these planets is also younger than the Alpha Centauri candidate by a large margin. HR 8799 system is approximately 30 to 60 million years old. Beta Pictoris is roughly 23 million years old. AF Leporis is estimated at 24 million years old. These are stellar infants compared to Alpha Centauri's 5 to 6 billion years. The enormous thermal luminosity of young giant planets glowing brightly with their formation heat is what makes them detectable at distances of tens to hundreds of parsecs. An old thermally faint Saturn mass planet at 1.34 parsecs represents an entirely different and far more challenging detection regime. A confirmed detection would therefore represent not merely a new data point in the existing catalogue, but a qualitative expansion of what direct imaging can achieve. It would demonstrate that the technique can reach old, cool, Saturn-class planets in the habitable zones of nearby stars. It would open the door to systematic surveys of other nearby Sun-like stars with similar sensitivity expectations. And it would transform Alpha Centauri A from a frustrating blank on the exoplanet map into the most scientifically productive nearby stellar target for follow-up characterization, the confirmation problem. Confirming an exoplanet is not the same as detecting one. The history of exoplanet science is filled with detections that did not survive the confirmation process, and the specific challenges of confirming a candidate at Alpha Centauri A are distinct enough from those facing other planet searches that they deserve careful examination. The standard for confirmation in radial velocity and transit surveys is typically a detection significance of at least 5 sigma relative to the noise floor, combined with independent reproduction of the signal by a second instrument or a second analysis team. For radial velocity planets, confirmation usually requires multiple complete orbital periods of monitoring to verify the period and amplitude are stable over time. For transit planets, confirmation requires typically 3 or more transit events observed with consistent timing, depth, and duration. These standards are well defined, broadly applied, and have successfully filtered out a large fraction of the false positives that plagued early exoplanet science. Direct imaging confirmation follows a different logic. A directly imaged planet candidate must first be shown to be co-moving with the host star. If the candidate moves across the sky at the same rate and direction as the host star over months or years, it is gravitationally bound to the star rather than being an unrelated background object passing through the field of view. Second, it must demonstrate orbital motion consistent with Keplerian dynamics around the host star, meaning its position, angle, and separation must change over time in a way that is inconsistent with a stationary background object and consistent with a gravitationally bound companion following a predictable orbit. Third, in the most rigorous cases, the candidate's spectral energy distribution, its brightness at multiple wavelengths, should be consistent with the expected emission from a planetary atmosphere at the inferred temperature and mass, rather than being consistent with a galaxy, a brown dwarf, or some other class of contaminant. For the Alpha Centauri candidate, co-motion has not yet been established because only one secure detection epoch exists. The 2019 near detection of C1 is at a different position from the 2024 Webb detection of S1, which is consistent with orbital motion, but the positional difference could also be consistent with 2 separate, unrelated background sources or with 2 separate artifacts from 2 different instruments. Establishing co-motion requires detecting the same object at multiple epochs with a secure astrometric baseline, showing that its motion tracks the proper motion of Alpha Centauri A across the sky. Alpha Centauri's proper motion of approximately 3.7 arcseconds per year is large enough that this test is in principle very efficient. A background object would shift by about 18.5 arcseconds relative to Alpha Centauri A over a 5-year baseline, while a gravitationally bound companion would remain at a roughly constant separation, modulo its orbital motion. The problem is that the 5-year baseline between C1 and S1 is precisely the kind of baseline where orbital motion and proper motion effects are difficult to disentangle without a rigorous orbital model. The team's approach of fitting orbits that jointly explain both positions is the correct methodology, but it also means that the co-motion test is not independent of the orbital model. You cannot confirm co-motion without assuming something about the orbit, and you cannot confirm the orbit without additional detection epochs. This circularity is broken by the 2026 prediction. An orbital model derived from the 2 existing detections predicts a specific location for the candidate in August 2026. If the candidate appears at that predicted location, the orbital model is confirmed, co-motion is established, and the planetary interpretation is strongly supported, all in a single observation. The strength of this test rests on the specificity of the prediction. The model does not merely say the candidate will be visible somewhere around the star. It specifies a range of angular separations and position angles that are consistent with the orbital ensemble. A detection outside that predicted range would challenge the model. A detection within it would be compelling evidence. The Nancy Grace Roman Space Telescope, expected to launch in late 2026 or 2027, adds another potential confirmation pathway. Roman carries a coronagraph instrument, the first dedicated space-based coronagraph designed for high-contrast imaging at visible and near-infrared wavelengths. Roman's coronagraph operates at wavelengths of approximately 575, 730, and 825 nanometers, with contrast performance expected to reach 10 to the -9 after post-processing. This is significantly deeper than Webb's Miri coronagraph at 15.5 micrometers in terms of raw contrast, though the relevant comparison for planet detectability depends on the planet's spectral energy distribution at each wavelength. A Saturn mass gas giant at 5 to 6 billion years of age reflects stellar light at visible wavelengths and emits thermally at mid-infrared wavelengths. Its reflected light contrast ratio at visible wavelengths is determined by its albedo, radius, and orbital separation. For a planet with a geometric albedo similar to Saturn's value of roughly 0.47, at 1.5 astronomical units from Alpha Centauri A, the reflected light contrast ratio at visible wavelengths would be approximately 10 to the -8 to 10 to the -9. This places it near, but not far above Roman's projected contrast floor, making a detection possible, but not guaranteed. If Roman's coronagraph achieves the performance required, and if the candidate is real, Roman could independently detect it at a different wavelength from a different spacecraft, confirming its existence without relying on any prior Webb observation. Ground-based, extremely large telescopes currently under construction, including the European Extremely Large Telescope being built in Chile with a 39-metre primary mirror, and the 30-metre telescope planned for Mauna Kea in Hawaii, will bring unprecedented angular resolution and light collecting area to direct imaging surveys. Their planned extreme adaptive optic systems and coronagraphic modes are designed to achieve contrast ratios approaching 10 to the -8 at small angular separations. For Alpha Centauri A, these instruments will eventually be able to probe the habitable zone at sensitivities below the current Webb threshold, potentially detecting Neptune-class planets, or confirming the candidate with spectroscopic data that constrains the atmospheric composition. Planets and the binary clock. There is an aspect of the Alpha Centauri observational campaign that most popular accounts overlook entirely. The observation in August 2024 was not simply timely in the sense of using the latest telescope. It was timely in a very specific, quantifiable, and cyclically constrained sense that makes this particular decade the best window for direct imaging of the system in a generation. Alpha Centauri A and B orbit each other every 79.91 years on an elliptical path. As they trace that path, their apparent angular separation on the sky, as seen from Earth, changes continuously between a minimum of approximately 2 arcseconds, reached near their periastron passage in 2016, and a maximum of approximately 22 arcseconds, reached near a pastron around the year 2055. The specific value of their apparent separation at any given time depends on both the binary's current phase and the projection geometry determined by the orbital inclination and orientation relative to Earth's line of sight. This orbital cycle has profound consequences for direct imaging observations because the angular separation between the two stars determines how severely Alpha Centauri B contaminates the region of the image where planets around Alpha Centauri A would be found. When the two stars are at minimum separation of about 2 arcseconds, their diffraction patterns merge almost completely. The scattered light from both stars fills the same region of the coronagraphic image, making it nearly impossible to achieve the reference star subtraction quality needed to detect faint companions at the angular separations relevant for habitable zone planets. The years around the 2016 periastron were, from a direct imaging perspective, the worst possible time to observe Alpha Centauri. Since 2016, the stars have been widening. By August 2024, the apparent separation had grown to approximately 10 arcseconds. This provided enough angular distance between the two stars that the coronagraph centered on Alpha Centauri A could achieve meaningful suppression of the primary star's light, while the secondary, at 10 arcseconds away, contributed contamination that was manageable through post-processing subtraction. The 10 arcsecond separation is not optimal, but it is workable. And it was the minimum practical threshold for the kind of coronagraphic observation Webb performed. The separation will continue growing through 2025, 2026 and beyond, reaching approximately 14 arcseconds by 2030 and approaching its maximum of 22 arcseconds around 2055. Each year that passes between now and 2055 makes the binary contamination problem slightly less severe and the direct imaging sensitivity slightly better. The upcoming decade and a half represent a steadily improving window that will not be available again until the mid-2100s. The convergence of this widening binary separation with the commissioning of progressively more powerful instruments, including Webb now, Roman in the late 2020s, and the extremely large telescopes in the early to mid-2030s, creates a sequence of observational opportunities that, taken together, could resolve the planetary inventory of Alpha Centauri A's habitable zone more completely than any single future observation. Each instrument that looks during this window benefits from a slightly wider binary separation and contributes an additional constraint on whatever orbits the nearest Sun-like star. Missing this window through lack of telescope time, instrument failures, or simply insufficient scientific prioritization would not be catastrophic. The next favourable window begins opening again in the late 2130s, assuming the instruments available then are at least as capable as today's. But the opportunity cost of delay is real. A confirmed detection in the 2020s or 2030s would allow decades of follow-up characterization while the binary separation remains favourable. A detection in the 2150s, in the next favourable window, would give any future scientist far less favourable follow-up time before the stars close again. This is why the 2026 reobservation is not merely scientifically interesting. It is strategically important in the context of a 79.91-year opportunity cycle. The window is open, the instruments exist, the candidate has been identified. Whether it is confirmed or ruled out in the coming years, the current era represents a scientifically unique moment. The first time in the 80-year binary orbit since modern exoplanet science existed that the stars have been wide enough, the instruments sensitive enough, and the theoretical framework mature enough to mount a serious habitable zone planetary survey of the nearest Sun-like stellar system, exozodiacal dust and what it hides. Alpha Centauri A almost certainly hosts some population of exozodiacal dust. This is not a speculative statement. Virtually every mature stellar system that has been examined with sufficient mid-infrared sensitivity shows evidence for warm dust in the inner few astronomical units. In our own solar system, the zodiacal dust cloud is a product of ongoing cometary activity and asteroid collisions. As comets sublimate their icy mantles near the Sun and asteroid belt objects collide and grind down, they release fine particles ranging from a few micrometers to hundreds of micrometers in size. These particles orbit the Sun, interact with solar radiation through the Poynting-Robertson effect, drift inward over timescales of tens of thousands to millions of years, and are eventually sublimated as they approach the inner solar system. The level of zodiacal dust in our solar system is not unusually low. In the context of nearby stellar systems surveyed by missions like the Spitzer Space Telescope and Herschel Space Observatory, our zodiacal cloud falls near the median of what is observed. Some nearby systems show dust levels tens or hundreds of times higher, producing so-called exozodiacal clouds bright enough to be detected and spectrally characterized. Others show dust levels comparable to or below our solar systems, invisible to the photometric surveys that have been conducted. For Alpha Centauri A, the August 2024 Webb observation placed an upper limit on the total integrated dust luminosity, rather than a detection of diffuse emission. The upper limit, expressed as a fractional infrared luminosity relative to the host star, corresponds to a dust density no more than a few hundred times that of our own solar system's zodiacal cloud. This is a relatively loose constraint. It rules out an extremely dense and hot inner dust disk, but it is consistent with a wide range of dust levels that could produce localized enhancements detectable as point sources. The relevance of exozodiacal dust to the S1 candidate is twofold. First, as discussed in earlier chapters, a compact dust clump could mimic the appearance of S1 in the coronagraphic image. Second, and more broadly, the level of exozodiacal dust around Alpha Centauri A has direct implications for the habitability of any planets that orbit there. Dense zodiacal dust clouds reduce the habitability of inner planetary systems through several mechanisms. The dust intercepts and scatters stellar radiation, altering the thermal environment of nearby planets. Dust particles collide with planetary atmospheres and surfaces, delivering material but also eroding atmosphere if the flux is sufficiently high. Most significantly, for future characterization efforts, dense dust clouds create a bright mid-infrared background that makes it harder to isolate the spectroscopic signal of a planet's atmosphere from the diffuse emission of the surrounding dust. For the planned future mission concepts aimed at detecting and characterizing habitable, Earth-like planets around nearby Sun-like stars, the level of exozodiacal dust around each target star is a critical input to the mission design. Concepts like the Habitable Worlds Observatory, which NASA's 2020 Decadal Survey in Astronomy and Astrophysics recommended as the highest priority large space mission for the coming decades, require target stars with dust levels low enough that the coronagraphic images are not confused by dust emission. A star with dust at 100 times our solar system's level would require significantly longer integration times or a larger aperture to achieve the signal-to-noise needed for atmospheric spectroscopy compared to a star with dust at 10 times our solar system's level. The Webb upper limit on Alpha Centauri A's dust level is not yet precise enough to definitively predict how favourable the star would be for the Habitable Worlds Observatory campaign. Tighter constraints on the dust level would require deeper mid-infrared observations, ideally at multiple wavelengths, to constrain the dust temperature distribution, combined with near-infrared observations to constrain the scattered light component of any dust disk. Each additional constraint narrows the range of dust properties consistent with the data and provides more reliable inputs for mission planning. In this sense, the Webb observation served multiple scientific purposes simultaneously. It searched for a planet candidate and found one. It constrained the exozodiacal dust level and placed an upper limit, and it characterized the technical performance of MIRI's coronagraph when applied to the system, providing a benchmark against which future observations and future instruments can be calibrated. The data from this single observing campaign will inform planetary science, dust disk science, and mission planning science for the better part of a decade, the nearest star and the nearest answer. Alpha Centauri's grip on human imagination has never required scientific justification. The system is visible, bright, and close. It appears in the mythology of cultures across the Southern Hemisphere. It anchors the opening chapter of every serious discussion of interstellar travel. It is the first place anyone points when asked what we would visit if we could leave the solar system. The emotional and cultural attachment to this system precedes the science by millennia. But the science, when it finally arrived in force, has complicated the comfortable narrative in ways that are only now becoming apparent. The assumption embedded in virtually all popular and much scientific thinking about Alpha Centauri is that proximity implies knowability, that the nearest Sun-like system must be among the most thoroughly understood planetary environments in the galaxy, simply because it sits so close. The Webb observation and everything that preceded it across decades of failed searches dismantled that assumption at its foundation. What the data actually show, taken together without narrative embellishment, is a system that has been resistant to characterization at every level of planetary science. Radial velocity surveys produced a false positive that was retracted after 3 years. Transit searches found nothing and face geometric limitations that cannot be overcome by any improvement in instrument sensitivity. Ground-based direct imaging produced an ambiguous single-epoch detection in 2019 that could not be followed up. Space-based direct imaging with the most powerful infrared telescope ever constructed produced a second ambiguous single-epoch detection in 2024, followed by two non-detections that the orbital models show are consistent with, but do not confirm a real planet. After all of this, the planetary inventory of the two Sun-like members of the nearest stellar system remains unconfirmed. This is not a failure of science. It is science working exactly as it should, applying progressively more powerful tools to a hard problem, recording what is found and what is not found, building models that make testable predictions, and refusing to advance speculative conclusions to the status of established facts. The process is correct. The result to date is simply that the problem is harder than expected. What makes the situation genuinely unsettling, rather than merely interesting, is the implication for our broader understanding of nearby stellar systems. Alpha Centauri is the hardest nearby Sun-like target specifically because it is the nearest and therefore brightest. Every other nearby Sun-like star is easier to observe in the technical sense. Fainter, less contaminating, less prone to saturating detectors and overwhelming coronagraphs. If we cannot characterize the planetary environment of the nearest and most studied Sun-like system with certainty, the implied uncertainty for other nearby systems is at least as large and likely larger given that they have received less attention. The solar neighborhood within 10 to 20 parsecs contains several hundred Sun-like stars with spectral types similar to the Sun's. Of these, a fraction have been monitored extensively by radial velocity programs. Fewer have been targeted by direct imaging surveys. Almost none have been observed with the mid-infrared coronagraphic sensitivity that MIRI-I brought to Alpha Centauri. The census of habitable zone planets around these nearest Sun-like stars is sparse, incomplete, and subject to the same selection biases that have made the Alpha Centauri search so difficult. Gas giants at 1 to 3 astronomical unit separations around old, mature Sun-like stars are essentially invisible to all current detection methods except direct imaging with mid-infrared coronagraphs, and those campaigns have barely begun. The Habitable Worlds Observatory concept, recommended by the 2020 Decadal Survey as the flagship space mission priority for the 2040s, is designed precisely to address this gap. A space telescope with a primary mirror of roughly 6 meters operating at visible wavelengths, with a coronagraph capable of achieving contrast ratios of 10 to the negative 10, could in principle detect Earth mass planets in the habitable zones of nearby Sun-like stars. The target list for such a mission would include Alpha Centauri A and B, though the binary contamination problem would require careful instrument design to manage. But the Habitable Worlds Observatory lies decades in the future. For the next 10 to 15 years, the combination of Webb, Roman, and the extremely large telescopes defines the frontier of what is achievable. Within that frontier, the Alpha Centauri candidate occupies a special position. It is the only direct imaging planet candidate around a Sun-like star at a distance below 5 parsecs. It is the only candidate in the habitable zone of a Sun-like star in the current direct imaging literature. And it is the only candidate that is subject to a specific orbital prediction that will be tested by a concrete observational program within the next year or two. All of this makes it singular in the current landscape of nearby exoplanet science, regardless of whether it turns out to be a real planet. The 2026 observation will not resolve everything. Even if the candidate reappears at the predicted position and brightness, confirming it as a gravitationally bound companion to Alpha Centauri A, important questions will remain about its nature. Whether it is a planet or a high albedo substellar object, whether it has moons, whether its atmospheric composition resembles Saturn's or something qualitatively different, and whether any smaller planets share its system. These questions will require years of additional observations to address. But a confirmed redetection at the predicted position would transform the current candidate from a scientifically interesting possibility into the most important single exoplanet target in the sky for the remainder of the 2020s and 2030s. And if the candidate is not confirmed, if August 2026 produces another non-detection that falls outside the range explained by the orbital models, the story does not end. It redirects. The team would then face the question of whether the 2019 and 2024 signals represent two independent spurious detections that coincidentally appeared near the habitable zone of the same star, or whether the detection methodology needs refinement to distinguish real sources from the artifacts of reference star subtraction in the most technically demanding observational context in nearby stellar science. Either conclusion advances the field. Either conclusion improves the methodology for subsequent surveys of other nearby Sun-like stars, where the same techniques will be applied with progressively better instruments. Alpha Centauri is, in this sense, not just the nearest Sun-like system. It is the proving ground for the methods that will eventually be used to characterize planetary environments throughout the solar neighborhood. The technical challenges it presents, the blinding brightness, the binary contamination, the inner working angle limitations, the ambiguity between dust and planets at current sensitivity levels are not unique to this system. They are the generic challenges of direct imaging around nearby Sun-like stars, expressed in their most extreme form, because this system is the nearest example. Solving them at Alpha Centauri does not just answer questions about one system, it develops the methodology, the calibration benchmarks, and the interpretive frameworks that will be applied to dozens of other nearby targets in the years that follow. The nearest star is not a solved address, it is a test case, the answer to whether it hosts a gas giant in its habitable zone, whether there are smaller worlds beneath the current detection horizon, and whether the nearest Sun-like stellar system resembles our own solar system in any meaningful respect is not yet known. But the instruments to find that answer are now operational. The observational campaigns are underway, and the question is more precisely formulated than at any previous moment in the centuries since humanity first looked up and gave this bright point of light a name. What that answer turns out to be may be the most significant thing this generation of astronomers learns about the universe within 10 light-years of Earth. The question that remains. Because Alpha Centauri A is only 1.34 parsecs away, any confirmed planet there would be uniquely valuable. The amount of light received from a planet decreases with the square of distance, meaning a planet around Alpha Centauri would be tens to thousands of times easier to study than similar planets around most nearby stars. Atmospheric spectroscopy that currently requires days or weeks of telescope time could potentially be accomplished in just hours. Instruments such as Webb's Mirror and NuSpec could search for water vapor, methane, ammonia, phosphine, and other atmospheric molecules, turning the nearest Sun-like star into one of the most information-rich planetary laboratories ever discovered. The scientific implications extend beyond a single planet. A confirmed gas giant would reveal whether the nearest Sun-like stellar system shares the basic architecture of our own solar system or follows a fundamentally different evolutionary path. Future observations could determine its atmospheric chemistry, temperature structure, and weather patterns, while continued searches might uncover smaller rocky worlds orbiting closer to the star. If Earth-sized planets are eventually found, their proximity would make them among the most accessible targets for atmospheric characterization in all of exoplanet science. What Webb discovered in August 2024 was not a confirmed planet, but something equally important, proof that such a planet can be searched for directly. A faint source appeared in the habitable zone, then disappeared in later observations, leaving its nature unresolved. It could be a Saturn mass planet on a favorable orbit, a transient dust structure, or an observational artifact. Whatever the answer, the observation demonstrated that the glare of Alpha Centauri A can be penetrated, and that meaningful searches are finally possible. After centuries of speculation, the nearest Sun-like star is beginning to reveal its secrets, and the next generation of observations may determine whether an entirely new planetary system has been hiding there all along.